Okie dokie. Today we're going to solve something called the fly problem. And that is, this spider has a fly problem. He needs to know how to get to the fly, which is over here inside a room, as fast as possible without being like Spider-Man and shooting his web and getting it. So he's going to have to crawl to the fly. Some people might say, hey, why doesn't the fly just go down the crack here and go along the diagonal? And that should be the shortest distance that the spider has to crawl. We'll find out that that's not the case. So let's assume that the spider is not going to crawl down here. If he's not going to crawl down this crack, he's going to have to crawl over here probably, and some distance x, which we're going to try to find out. If that x turns out to be 0, then he should come down here. But if x does not turn out to be 0, then he should not. So let's figure out this first distance that the spider goes. We're going to have this distance could be a of the room is a high and b long and c wide. So this distance right here will form a right triangle right here, a, x, and d1. And so d1 right here, the total distance is going to be d1 plus d2. That's this. So d1 with this triangle with the legs of a and x squared, of course, d1 will equal the square root of a squared plus x squared. If we look at d2 here, this distance right here is x, but all of this is b. So if this is b and this is x, then this distance from here to here must be b minus x. And so this distance is b minus x, and this is c, and this is, of course, is a 90-degree angle. And so here's our hypotenuse, d2, with b minus x, and c is the legs. And so d2 will equal the square root of c squared plus the square root of b minus x squared there. So we have the total distance. D total is this plus d2, d1 plus d2, this hypotenuse plus this hypotenuse. All right, we used Pythagorean's theorem to figure those out. If you want to minimize this distance, obviously you want to minimize this distance, you'll have to take the derivative of this with respect to x, of course, and set it equal to 0 and solve for x. So the derivative of this, of course, is this. I'm not going to teach you derivatives. You can learn at some of my other lectures, or read a calculus book, or watch a calculus video. So we'll solve for x here. We set this equal to 0. If we scoot this over and scoot this over, do a little bit of algebra on this, you'll get this. Do a little bit of algebra on this, well, a lot of algebra on this, and you'll get this. And if you, of course, you do some algebra with this, you get this. This is a quadratic with x, so there's x squared, x, and no x. So you'll have to solve this with a quadratic equation. It's quite a mess. Sorry about that. I'll show you how bad a mess it is. Just to show you, I don't know why I'm doing this, but just to show you here, we're at we have this step right here. If we do algebra to this, we get this. If we do algebra to this, we get this. If we do algebra to this, we will get this. Then we can solve the quadratic equation with this. We get this. This simplifies to this. This simplifies to this, and this simplifies to this. Okay? So there's all the algebraic steps to get to there. I just didn't want to waste 50 minutes of your time doing the algebra for that. Okay, and so when we solve for x here, we'll get this as our answer. Let's just do an example. We'll make A be 3. The room is 3 whatever meters tall. It's 4 meters long and 5 meters wide. And if we plug these three things, A, B, and C, into our equation, we get this, and this becomes this, and that becomes a 1.5 meters. So x is not 0, so that means that the spider should not go down this crack and go across the diagonal. He should make x be 1.5 if this is the 4 right here, and this is 5 and this is 3. If there's different values, of course, x will be a different value for different rooms. So this needs to be 1.5, so he needs to head at a distance here so that this is 1.5, and then head straight for the spider, and he'll have minimized the distance that he walks. So we might notice that we can see it might at first seem like it's strange that he would have to do that, but if we look at our spider, if we look at our room at first, I'm sorry, I'm drawing a spider and a fly. And then we look, should have done this before, I apologize. Okay, so if we notice here, here's our spider and here's our fly, and people who say, why doesn't he just come down this way and down that way, notice that if we pull this wall down, it goes right here, pull this wall down, it goes right here, so that now the spider that's over here when it's on flat land will be over here. Well, somebody saying, hey, just go down the diagonal and go along this diagonal is saying, hey, spider, why don't you do this and then go that way? And here we can really see that that would be the much larger distance than if the spider went here, where this distance was 1.5, and shot straight across. It can be called the geodesic of this scenario right here. And we get the first inklings of Einstein's general theory of relativity. We get starting to learn about geodesics, which are the paths of minimum length from one point in a three-dimensional object that's put in 2 dimensions from one point to the next point. Okay, so here it's obvious that the spider should go in some weird path, which is very similar to this path right here. We can visualize that. Okay, I think that's long enough, and I hope you enjoyed this lecture, and I hope you thank you for watching. I welcome any comments at the bottom. Thank you. Bye.